Recurrent neural networks can do prediction or generation based on series data. Example Gladia, it can predict the stock price or generate a sentence for a given paragraph. Compared with other neural networks, RNNs don't ask for a fixed length input, so that you can input a dataset paying no attention to unifying the length, such as an article or an audio. This is the reason why RNNs always tackle NLP tasks, or make recommendations based on users' behavior. If you are new to RNNs, the inside of it could make you perplexed. Now let's start from a basic neuron. For most neural networks, the direction of the propagation is forward only. However, the propagation of an RNN is bidirectional, both forward and backward. The most simple example is a recurrent neuron receiving an input xt and output at the previous moment y-1. Now, let's fasten with a temperature prediction example. Provided we have a series of data about temperature and wind speed in the last 6 days, we're going to use a recurrent neuron to predict tomorrow's temperature, based on temperature and wind speed data we have already known. This neuron has 3 inputs, from x1 to x3. However, the x3 is empty initially and updated by the previous output of this neuron. First of all, the neuron received the temperature and wind speed on Sunday, x1 and x2, and predicted Monday's temperature as 19.8, which is incorrect but good enough. It's not far from 18.8. Parameters in this neuron would be updated by the backpropagation. The result after the activation function is the output at that moment, and also stored in x3. Next, the neuron received the Monday's data. At this moment, the x3 is not empty because we have got an output at the previous moment, 19.8. And the neuron predicted Tuesday's temperature as 17.4 based on 3 inputs. If today is Tuesday and we are going to predict the temperature on Wednesday, it's easy to understand that there are 3 inputs. 2 of them come with today's data, and 1 come with Monday's information. More strictly, it comes with more information that 17.4 is the result based on Sunday's data, and we just compress all info into yesterday's output. Let's replace the x3 by yt-1, as it always comes with information about yesterday. For the x1 and x2, they are from the dataset, stored in the dataset, but yt-1, this is the result, stored information before this moment, which makes the neuron remember things that happened. We can allocate one variable, named memory cell, to store the value. Say, the neuron predicted Wednesday's temperature as 18.3 and output this value. Meanwhile, this value was also delivered to the memory cell. And then the neuron received Wednesday's data and records the last output from the memory cell. It worked as before, which allowed all 3 inputs, containing 2 info from data and 1 from history. In fact, the memory cell could be considered as a part of this neuron. It is the variable of this object, storing the last output and being updated at each prediction. Here, we have a neuron with a memory cell. It receives only 2 inputs from the outside and deals with 3 values de facto. And this is basic recurrent neuron. Let's construct the formula for a recurrent neuron's output at moment t, denoted as yt. First of all, collect the input data as a vector, say x1, x2, the temperature, the wind speed, etc. There could be the features from the data, or the output from the previous layer. Like other neurons, the recurrent neuron has a weight vector to merge these inputs. Then, the memory part. The recurrent neuron has a memory cell, which stores the output at the previous moment t-1. There is also a weight for the previous output. The neuron merges input xt and the previous yt-1 and the bias together. Finally, the activation function calculates the result of yt. The activation function here is important, by the way, in that recurrent neurons suffer from exploding and vanishing gradient problems. The range of the derivative of thun is from 0 to 1, which is better than sigmoid's range, from 0 to 0.25. It's easy to build a layer consisting of recurrent neurons. Let every neuron receive both the input xt and the previous output yt-1. Every neuron has two weights, wx for xt and wy for yt-1. For the whole layer, the output can be described as this formula. We can concatenate x and y as one vector, and this is a recurrent layer. The approaches of leveraging RNNs are flexible. You can choose a particular mode while ignoring some input or output. For instance, RNNs can generate a sequence's output by learning from an input sequence, which is called seek-to-seek. If we collect the last output only and ignore all others, the network de facto converts a sequence to a vector, either seek-to-vec. This is often applied to convert a comment to a score. Also, the neglect of other input but the first one makes the input being a vector, and thus the network now can transfer a vector to a sequence, either vec-to-seek. You can also use the same vector and input it many times to do the vec-to-seek. Last, you can use a seek-to-vec as an encoder and connect a vec-to-seek as a decoder. This paradigm is ubiquitous in translation tasks. First, input a language sequence. Then, the encoder converts it as a vector. Finally, put the vector into a decoder and it returns a sentence in the target language. The encoder-decoder paradigm circumvents the problem of the unpredictable length of a sentence during translating. It doesn't care about the length.